All right, let's get straight into it. This is your revision explainer for energy transfers, a really key topic from the AQA GCSE Physics spec. We're going to break down exactly what you need to nail for that exam.
Okay, so here's how we're going to break it down. We'll start with the basics of electrical power, then see how our everyday appliances actually use that energy. After that, we'll zoom out to look at the massive national grid, and we'll finish up with a super quick summary of the key formulas you have got to remember.
Right. First things first, electrical power. Honestly, this is the foundation for pretty much everything else in this topic, so let's make sure we're crystal clear on what it actually is and, crucially, how we calculate it.
So in simple terms, power just tells you how fast a device is using energy. Think about a 100-watt light bulb. What that really means is it's transferring 100 joules of electrical energy every single second. It's all about that rate of transfer.
Now, for your exam, you've got to know two key equations for power. Which one you use? Well, it just depends on what information they give you in the question. If you've got voltage and current, you're going to use P equals VI. But if they give you current and resistance instead, then P equals I squared R is your go-to formula.
And seriously, I can't stress this enough. You're expected to be able to just recall both of these and apply them. So, get them on a flashcard, test yourself, and make absolutely sure you know what P, V, I, and R all stand for, and their units. So now we've got a handle on power, which is the rate of energy use, right? Let's take the next logical step and look at the total amount of energy transferred by our everyday appliances. Every single time you flick a switch, a voltage is providing that push to make electrical charge flow around the circuit. And as that charge moves through something, like a light bulb or a motor, it does work. And that's how energy gets transferred into something useful, like light or sound or heat.
And yep, just like with power, there are two main ways to calculate this energy transfer. E equals PT is perfect if you know the appliance's power rating and how long it's been on for. In fact, that's pretty much what your electricity bill is based on. The other one, E equals QV, connects the energy directly to the amount of charge that's moved and the voltage that was pushing it.
Just think about it for a second. A blender and a toaster both plug into the same wall socket, but they do completely different jobs, right? The blender's motor is all about converting electrical energy into kinetic energy to spin those blades. But the toaster's heating element is designed to turn that same electricity into thermal energy. It's the same principle, just a totally different end result.
Okay, let's zoom way out. We've talked about a single appliance, now let's talk about the gigantic system that powers all of them, the national grid. This thing is a massive piece of engineering, and you really need to understand the physics that makes it all work.
At its heart, it has one job and one job only: to move mind-boggling amounts of electrical power from where it's made to where we need it, and to do that as efficiently as possible over hundreds of miles of cables.
So this whole journey happens in 5 key steps. First, the electricity is generated. Then, its voltage gets stepped way up for the long trip. It travels through all those cables you see on pylons. And then, right before it gets to you, its voltage is stepped down to a safe level. And the real heroes of this whole story are the transformers.
And this comparison is absolutely vital for your exam. To keep the power constant, if a step-up transformer makes the voltage go up, the current has to go down. It's an inverse relationship. And then, the step-down transformers near our homes do the exact opposite. They drop the voltage way down, which then increases the current to a useful, safe level for our appliances. And here it is. This is the big why. The whole reason the system is designed this way is to minimize wasted energy. We step the voltage way up, which, because P equals VI, makes the current drop right down. So why do we want a low current? Well, because the energy lost as heat in the wires is calculated by P equals I squared R. If that I is tiny, then I squared is even tinier, which means an exponentially smaller amount of energy is wasted as heat. That is the secret sauce to the national grid's efficiency.
Okay, we have covered a lot of ground there, so let's do a super fast recap of the 4 essential equations from this topic that you absolutely are expected to be able to recall in your exam. There they are, your 4 non-negotiables, the 2 for power and the 2 for energy transferred. You've got to make sure these are absolutely locked into your memory for the exam. They are completely fundamental to this entire topic.
So to wrap this all up, here's a final thought. Have a go at answering this classic exam question. Can you use the equations we've just covered to put together a perfect 2-part answer? You'll need to think about the link between P equals VI and P equals I squared R. If you can nail that explanation, you've totally mastered this topic.